Okay, we're in conservation topics at this point, and we're going to start with the concept of work and how that can be used to change the energy of an object. Work is defined as the amount of force applied to an object over a distance or a displacement, and then that will determine the amount of energy that's added or taken away from an object. So we do work on an object to increase or decrease its energy. We can do that with heat sources. So we heat something up, we're doing work on it. Right now we're talking about mechanical sources, so applying forces and pushing or pulling different things to different points and looking at how much energy they gain or lose. Okay, an impulse is a force acting over a time. Again, impulse comes from the concept of F equals ma, the second law of motion. Work is also a force, but instead of working over a certain amount of time, we talk about working over a certain amount of distance. And the farther that distance is, the more work is done. The work will then cause a change in the energy of the object. And so it will increase or decrease the energy in some way if work is actually done. Okay, and number 2 here, second part, we're just looking to see if we think work is done. In all those cases, it's important that you identify the object. When we talk about work, we're talking about an object. In the first one, if we apply a force to a wall and the person pushing becomes exhausted, have we done any work? And the answer would be no, and that's because the object that we were pushing on did not move. Since it did not move, the distance is 0, and if the distance is 0, then the work done is 0. A weightlifter lifts a barbell over her head. Again, what's the object that we are interested in? Here it's the barbell. The barbell does go up. The weightlifter is pushing up. So in this case, yes, the barbell is moved by the person's push. So the applied force made the barbell move up. A waiter carries a tray full of meals across the dining room at a constant speed. Okay, now this gets a little trickier. If you're going to carry the meals and it's a constant speed, what you're actually going to be doing is applying your force upward on the tray. So we're interested in the tray. So the waiter is actually pushing up while the motion of the tray is across the room. Now that means that the force and the displacement or distance are at 90 degrees to each other. And the cosine of 90 degrees is 0. So in this case, although there is applied force and the object is moving, the applied force that we're talking about, the waiter, is not the thing that's making the object move in its direction. It's really moving just because of inertia. We're balancing the forces and nothing more. Okay, D, a rolling marble hits a note card and moves it across the table. Again, what's the thing that we're interested in? In this case, I would assume the note card. We're going to do work upon the note card and add energy to it. The note card does move. It moves because it's being pushed by the marble, so at least during the time of the impact there is some work done, so we'd have to say yes. The card has an applied force upon it from the interaction with the marble, and it does move. So yes, work is done. Shot putter launches the shot. Again, I'd be most interested in the shot as my object. Now the shot putter is going to apply a force, and then the shot put is going to start as a projectile and fly out here on its own. Now, while the shot putter is pushing, is increasing the energy of the put of the shot, and therefore it's a big yes. We can see that in part because we know the ball is going to rise. That's an increase of energy is needed to make it rise. It's also going to speed up while it's being pushed. Increasing speed is an increase in energy. Okay, now, work, unlike momentum and impulse, is a scalar. Direction doesn't matter, although we often talk about positive work or negative work. In this case, the positive or negative is not about the direction, it's about whether we add energy, or subtract energy. If our work is positive on an object, then the energy of that object should go up. If it's negative, then it should go down. So it's a scalar, and the plus or minus will tell us whether it adds or removes energy from the object. Okay, in terms of units, work is a force, which will be measured in newtons, times the distance, which will be measured in meters. So the base unit is its newton times a meter, and that's a derived unit. The newton itself is a derived unit. It's made up of meters and seconds squared multiplied by kilograms. So we can take it one step lower. It's made up of a kilogram times a meter per second squared times a meter, or kilograms times meters squared over second squared. Now 1 newton times 1 meter is defined as the work done by 1 joule, or is 1 joule of work, which is equivalent to gaining or losing 1 joule of energy. So, the joule is a unit of work, newton times the meter is the unit of work, and kilograms times meter squared over second squared is also a unit of work. Now, the joule and the newton meter tend to be used interchangeably, and we more often think of newton meters when we talk about work, and a lot of times we'll talk about joules when we talk about energy. But again, 1 joule is equal to 1 newton meters worth of work, so they are equivalent to each other in every way. Okay, so that's going to finish our first episode. We'll wrap up the second episode and second page next time.